So this is a sort of a study of how do you get TPMs and SEDs to work together. And I'm going to give you sort of a abstract sort of introduction to the problem, and then I'm going to jump into the details, and the details turn out to be really, really interesting. Okay. So the talk is basically in two pieces. One piece is sort of the overview of this, and then the next piece is the details of the implementation and so forth and so on. And this is actually about 3 specifications, not 2. Okay, so it's about the self-encrypting drive, which is sort of Opal 1, Opal 2, so forth and so on, which Dr. Willett went over in some detail for how they work. Okay, the trusted platform module, which Dr. Challenger went over, and then putting it together in a T&C network. So this is the three TCG specifications and how you bring them all together in one system. So the way to think about this is this is an IT environment. So the idea is that you're a large corporation or a large organization and you want to see how to bring all these pieces together. Okay. And so I made up 3 terms in the use case terminology, which is something I call central distribution, a fielding site, and then an end user PC. So there are 3, from a security model perspective, there are 3 pieces to this. Okay. The central distribution is essentially the intake. So when a corporation starts getting PCs coming in, they run through the intake for there could be a single location for a corporation. It could be different locations within the corporation, but it is a high security, high assurance location. Okay. The fielding site is a trusted, secure location. Think of it as, if you're a large corporation, a fielding site might be the IT in your offices, your branch offices, or your manufacturing facility, whatever. Okay. So the fielding site is sort of this next level down. Okay. It's very conceivable that you could have your central distribution, if you're a small enough company, your central distribution and your fielding site in the same place. But different things happen, so you're required in this thing that your central distribution be extremely high security. If your fielding site happens to be extremely high security, that's okay too. Okay? And then the end user PC is what I call a moderately trusted and moderately secure location. And at this location, all things that are called authorities and credentials are fixed, except the user password is kind of an idea. So the user can change his password, but there's no administrative privileges in the system at all, okay, at the end user PC type thing. And what I'm going to do is show you all how to make this stuff sort of work together. So this is pretty much what Michael's already talked about. This is SED was as secure data storage. 100% of the data written here is encrypted. It has a certain characteristics and so forth and so on. And TPM security is associated with the motherboard itself. There's 2 main things that we look at the TPM chip for. One is public-private key pairs that are hardware-protected private key operations. So the idea is that, and in fact, in the stuff that we're going to do in terms of bringing all these pieces together, the private keys that are minted for the TPMs are non-migratable, all of them. So in designing this enterprise scheme, there's no such thing as a private key that escapes from a TPM. The other one is that we're bringing on the TPM is the PCRs, the platform configuration registers, for guarded PC health measurement. So we're going to get the whole PCR scheme to work with the SEDs and the TNC and so forth to bring it all together. Okay. By the way, at the end of the show, okay, I'll give you byte counts of the number of bytes that have to be transmitted over the network in order to completely run this system. So you can see actually how efficient the system can be made, and so forth and so on. So this is okay. So there's two slides that show at a very abstract level exactly what happens in normal use and in provisioning. And so this is a very key slide. So TNC is Trusted Network Connect. That's the way you decide whether you're going to allow that PC to show up on the network and so forth. And the TPM is going to be providing a non-spoofable device ID, so it will provide a globally unique non-spoofable device ID to the network, so a bad guy can't come in and come up with another device ID. And it'll provide device preboot health in order to allow TNC to allow network access. The TPM, with the SED, there's a sort of a preboot unlock key. So most of the time this is somebody typing on preboot, and it unlocks the SED. But the way we're going to bind the SED to this motherboard in this specific TPM is the TPM is going to supply an additional unlock key. And then the way it's going to actually work is the two keys get XORed with each other, and that becomes the effective key that will actually unlock the SED. Okay. So the idea is that without the TPM knowing its secret and the person knowing his secret, the SED does not unlock. We do not get, the system doesn't come up. Okay. And then, once the SED is unlocked, the TPM, the BIOS is still writing PCR registers and so forth. The SED is unlocked. It's coming up as a full-scale computer. Okay. And it reports itself out as a test to the network and says, I came up, I'm safe, everything came up correctly, let me on the network. Okay. So this is the normal use. It's a very simple kind of a model. So this is the provisioning. And the way to think about provisioning is there's central distribution, which is super high security provisioning. And then there's fielding, which is much less security in provisioning. But this is the fundamentals of how provisioning sort of takes place. Okay. So somebody learned how to go backwards. So this is central distribution PC setup, and device health parameters are basically sent to the TNC stuff to let people know that these are what the PCR values should be for a healthy PC. So it's set up into the TNC network that it can look at and say, yeah, this is a healthy PC. The central distribution setup will also create a TPM passcode, a key pair, and some certificate creation. And and something we're calling the disduplication. Passcodes will be provisioned for unlocking and managing the SED. And additional passcodes will be generated for the TPM so that it has an SED unlock key as well. So in provisioning, you're putting all the keys into the system. And in this is essentially what happens in central distribution, is all the sort of core keys are created. Okay? And then the system is locked down. We'll get into what happens in central distribution a little bit further in a second. So one of the problems that this system solves, okay, is what happens if you have a PC with just an SED and no TPM on it. But if you have an SED and a TPM, but no T and C network access. What happens if you have all three? What happens if you have a TPM and T and C but no SED? So the system sort of has to work all the ways. It has to make the maximum use. It has to have the maximum gain in all cases. So whatever you get out of the SED, if you've got an SED, you get it. If you've got a TPM so that you can lock the SED to the motherboard, you get it. Okay. If you don't have network access control, you still get all the benefits of what the SED does and the TPM does without the network access control benefits. So the idea is you can mix and match any combination of the TCG specs. They all work together just fine. So here's a little more detail in the central distribution, the fielding site, and the PC. Okay. Central distribution is done once for the entire life of the PC, TPM, and the SED, but it's not required that the SED be mated to the motherboard yet. Okay. But the initial provisioning is done once, and what we're going to be basically doing with these things is setting up very large random numbers as passwords that have the ultimate authority. Okay, so in central distribution, there's a database that's kept of all the SEDs that have been provisioned, all the motherboards that have been provisioned, and the super secrets for how can you get at these things. They're kept in central distribution and never leave central distribution at all. So if you want to go reset your machine, you either put it in a garbage can, okay, or you send it back to central distribution for resetting it at this level. Okay. The fielding site is where certain administrative credentials can be employed and user credentials can be changed administratively. So this is not the highest level of administrative control, but a second level down in administrative control. So, for example, in the fielding site, you can erase a drive. You can cryptographically erase a drive. Okay? Whereas at the PC level, the average employee can't erase his drive. He can try. Okay? He just doesn't have the credentials to do it. So this is more of the sort of the life cycle of this thing, and among the things. So here's showing the secure erase can happen at the fielding site. It can't happen at the PC level. When you call these things fielding sites, this is not necessarily for central distribution. It's very likely to be a separate place with. The fielding site, it could be IT administrative control over the network down to the PCs, okay, that are in people's offices and so forth, or laptops. For central distribution, we really require that the physical device be there, because there are going to be secrets that are going to be available that if you start putting them over the network, these are bad ideas. Okay. Okay, so that was the overview, the general idea of this. So the critical idea is there's a central distribution, fielding site, and the end user PC. And then what I'm going to show y'all in the voila world, okay, is I'm going to show you that the way the credentials are set up for SEDs, credentials are set up for TPMs, match exactly this kind of three-tier level of management, okay? And so they match up just perfectly, and then you can do fun things like getting the things to work together. So this is the Opal spec, Okay. And what is going on here is there's two levels of administrative credentials in Opal. Okay. One level is something called the admin SP administrator, the SED, or the drive owner, depending upon who's writing the spec on which week. Okay. But this is the super password. This is the, if you know this, the admin SP administrator, you have ownership of the drive. You can basically do anything. Okay. He can create or delete what's called locking SP administrators. And under the Opal 1.0, whatever it is, I think it's up to 4, but most drives will do more than 4. These are the administrators of the encryption function itself, not the owner of the drive, but the encryption functions themselves. So these are administrative guys. Okay, and the administrator guy can create or delete users. I think in 1.0 it's 8. Okay. And he can also assign locking roles. So the administrator, the locking SP, can say, I want to take the drive and I want to divide it into 4 partitions. And this partition will be read-only, and it will be locked using this password. This partition will be read and write, and will be locked using this password, this user password. This partition will be locked, so forth and so on. It turns out the locking SP administrators can also do essentially what users can do. And this is in the fielding side, so it's got to be a reasonably secure facility because a locking SP administrator can create new users. Okay? And so you want to keep that in a modestly secure facility like the IT group in the company and so forth and so on. The guy who knows this 32-byte password, okay, can do anything to the drive. And so that 32-byte password never leaves central distribution database. It just does not leave it. It gets put on the drive, set to a large random number, and it's essentially God on the drive. So in this model, we've got a locked SED has 128 megabyte pre-boot area. And in its central distribution, the pre-boot code is put on the drive and made to be read-only. And also the drive is set with the admin or user passcode. And the fielding side guy can later do a crypto erase on the drive when it's unlocked and making it up as 256 gigabytes. And the user can also unlock the 256 gigabyte thing. So this sort of tells the whole story on how Opal works and the levels of user authorities and how they get together. So TPMs, when people talk about TPMs, they often lead people to believe that TPMs don't use passwords, but they do. Okay, with the SED, the passwords are 32 bytes. They can be large random numbers. Okay, with TPMs, TPM 1.2, the passwords are 20-byte passwords. So it turns out TPMs have the same sort of 3 natural levels of security associated with them. So the auth owner of the TPM can basically do anything. He's God over the TPM. Okay? He can, if you know the auth owner, for example, you can completely reset the TPM. You can change all the keys that it's keeping. You can do anything to the TPM you want to do. Okay? So again, in the central distribution, these keys, here's the set of keys that are created only in central distribution. So the auth owner key is created, that's kept secure. And then a bunch of other key pairs are created. So these are public-private key pairs that are created. One is something called the endorsement key, which is in public-private key cryptography, public key cryptography, the endorsement key is, the public key is an encrypting key, and the private key is a decrypting key. And so the endorsement key is needed to make all the other keys. So you make an endorsement key. This is in central distribution. So now using the endorsement key, you can start with the right authority, the right passcode. You can come in and start telling the TPM to make some more key pairs. Remember, in this, all of the TPM key pairs that are made, every one of them, the private key can never leave the TPM. So it'll be unique to the TPM. These will not be migratable keys at all. Okay. You have to have an EK to make something called an attestation identity key. And if y'all remember, we need to provide a unique identity for the motherboard out to the TNC, and this is what's actually doing that. And then you really sort of have to have the EK and some of these things so needed to certify this, but you also need to be able to make what's called a storage key. And in this particular case, we're making a non-migratable storage key, but this is not the storage root key. So this is from Challenger's talk. This is just a storage key that's used to keep some secrets. It happens to be one of the secrets it keeps is how to unlock the SED, how to mate the motherboard and the SED together. So performed on every boot of the PC, there's a pre-boot PC BIOS, which we've already sort of talked a little bit about. It'll hash pre-boot firmware and configuration settings and put them into appropriate TPM PCRs. And then the OS gets booted once the drive is unlocked. The TPM signs the PCRs using the AIK. And the OS sends this as a certified non-spoofable pre-boot health measurement for TNC. And it also sends if TNC is given it a nonce, it'll sign with the AIK and say, I'm really me. Okay? And here, and I've also signed these measurements. Okay? So here's another bunch of stuff that's only created in central distribution where the security is incredibly high. Okay? These are certificates that are made that prove the meaning of certain of the public keys that are used in the normal environment. And there's a root certificate that's self-signed by that's a true root. And then it has so it's typically signed by the manufacturer. So if you're pick a manufacturer, Infineon, they'll have a self-signed certificate, which should be themselves. And then they can sign the EK to say this is really a true TPM. Okay. There'll be a root certificate that can be self-signed, and it can be signed by the org. The AIK certificate will be signed by the org. So the guy cares about who the identity of this device is. So if you think of this is a root certificate for the manufacturer of the TPM. This is the root certificate for McDonald's. Okay? And they're worried about these are all my machines and nobody else's. Okay? And then the storage certificate will be signed by the AIK to prove that this storage certificate is really associated with this one TPM and no other. Okay? So now you've got the whole chain of identity established, and it's all real clear and everything like that. So I keep always wondering why I have this slide up. Okay, so so I got 2 or 3 slides here that these slides everybody will get copies of, and these are for sort of background readings. So this is the first of the sort of background reading slide if anybody ever wants to study this and get more detail on it. So this lays out, and it's not completely required that you do this, but so if you've got 4 partitions on the self-encrypting drive, this basically says what the admin, and this is the fielding level, the locking admin SP can do, and what each of the 4 partitions do. So there's a read-write partition, which is for the OS. There's a read-write partition for data. And there's a read-only, the user can only read, but the administrator can read or write it, and it can create an OS backup partition. So now, from an IT perspective, I can, if the user machine sort of OS blows up in Zimbabwe or wherever, okay, he can restore from the read-only partition, he can restore his OS and try to get the machine back up. Okay. And then we've got an imaginative forensic logging partition. So with terabyte 2.5-inch drives, what's 100 gigabytes on fragments? Okay. And so Michael's going to give me his terabyte drive and we can try to prove this at some later time. These are set up for write only. So you can write the partition. The user cannot do anything but have the system is going to be writing that partition. Okay. And what you write in that partition is going to be associated with forensics and controls that you might want from an IT perspective. Another little trickery here is in the pre-boot operation. One of the things you may want to do is do things like update certificates and so forth. So there are things that you can do in pre-boot that can sort of keep the whole family of activities working well. But most all the time you don't do that kind of stuff. Okay. So here's the security model for the SED and TPM deployment. And this is, again, one of these things you can read later. But there's some very interesting properties of this. One of them is once the SED is installed on the PC, there is one secret passcode for the user. So even though you can have 4 users or whatever, just one. Okay. If the TPM is not present, provision is made to use this to unlock an SED without a TPM. So there's a mechanism, I'll show it to you in a second, where if the TPM isn't there, the whole system just works. All secrets used on the PC have limited value. Okay, so the secrets that a user has, the passcode the user has very limited value. So he can be an insider, and it's very hard for him to escape the system that's been built for him. And then we have allowance for something called disk duplicators here, which are devices that can duplicate not only all the user content on the drive, but all the security areas on the drive too. And those are at the fielding site level. Those are not central distribution. And then a piece of trickery that's done here is normally people consider passcodes very weak. Okay. Well, it turns out in this whole design, all the passcodes except the user passcode code are large random numbers. So 2 to the 20th power and 2 to the 32nd power is the size of the field. So you're going to have like 10 or 15 passcodes being used. Okay, but they're all very large random numbers, and they're not available to the user at all. Okay. So unlike most passcode systems, you can have one weak passcode, but remember, if you've got the TPM sitting there, having a second passcode that's XORed with the user passcode, the entropy of the two passcodes is equivalent to the entropy of the highest entropy passcode. Okay. So if the user uses the password, okay, the secret that's held in the TPM to unlock the SED is a full 32 bytes, which is, pick a number, 240 bits, 220 bits worth of pure entropy, and it's not going to get guessed. Okay. So what you've done is you're actually creating a system that maybe if you've got a hold of the system, the guy used the word passcode, he can type in passcode and get it unlocked. Okay. But he can't change any of the parameters of the system. And if he tries to take the drive out and use it on another motherboard, good luck. So here are the TPM passcodes that are used. There's the endorsement key, which is the identity of the TPM, essentially. It's got a certificate associated with it. The name of the passcode is called ONORAUTH. There's a storage root key, which I didn't mention earlier. It's sort of created, but it's got a certificate. It's got a ONORAUTH to create, delete, or change the value of the storage root key. It's not unique. It's really, in this system, it just sort of comes along for the ride. The attestation identity key is a signing key. It's got a certificate associated with it. It requires ONORAUTH to create, delete, or change the value. It's unique to the TPM. It's only done in the central distribution. And then there's a storage key, which is done at the fielding site. Okay. And it's an exchange key, and it's got a user auth on it. So what you're going to see is the user password actually unlocks the storage key. And the storage key is hiding the split for the SED unlock key. So here are the SED passcodes. There's the SED, which is you own everything, done to central distribution. There are 3 admins that are set up. So one admin that's set up is something called transfer region. So I'll use an admin to go from one fielding site to another. So I can take a SED, and I know that I've got a way to the other fielding site and open up that SED using the transfer key. Okay. Just as examples. Here's the crypto requirements on the passcodes. They're all big random numbers, okay, except one, which is a memorable passphrase, which is user 1. Okay, and he can unlock the ranges with that passcode. So in this particular case, the passcode for unlocking the ranges is always the same passcode. So all 4 of the ranges he can unlock. And that's how this piece of the puzzle works. So here's the unlocking situation. Okay? So if you've got a PC that only has an SED on it, the user 1 passcode comes down here, and it just unlocks the SED and drives unlocked it. He's got his machine. Okay. if you've got a TPM and an SED, the user passcode unlocks the SED data store, which hides an SK, a storage key passcode, which unlocks the SK blob, okay, which pulls the TPM split out of it. These are all now. And then that split is XORed with what the person, his original user one passcode, okay? And then that unlocks the SED for access, and you're done. Of course, all this happens in a fraction of a second, so this takes no time to happen. But I've now caused the one user passcode to unlock everything and guarantee that I've got a binding between the TPM and the SED. And the binding is done through 32 or 20 byte random numbers that the user doesn't have access to. So this is one of the other slides that is for later, your later enjoyment. Okay, a lot of detail on how you make all this stuff work. And this is the third one. Okay, so this is the fun stuff. Okay, so this is TNC provisioning at central distribution. So what you want to do with the PC is basically you're going to make the AIK. You're going to get the AIK from the AIK certificate. You're essentially making the AIK for the public key for the AIK, putting it in the main database server. And you can request what we're calling a medium report, which will give you the PCR values off the machine, so you now know what a healthy machine is, because it's in your high security area. You're taking the measurements of it to have the golden values and so forth and so on. Okay. And it turns out miraculously, okay, this is costing you to store this data. This is costing you maybe 60, 80 bytes. So you're storing maybe 80 bytes to have the characteristics on that PC, so you can do 100,000 PCs, a million PCs, and keep it all in a very small terabyte SSD. And this is generating a sort of a small report. So you've got a main database server, the PC, and the sort of cloud. And the cloud is requesting a small report from the PC. PC gives the report to the cloud. The cloud gives it to the main database, the TNC thingy. The PC is allowed to go on the network. And the byte count to do this is 296 bytes and 49 bytes. That's your network traffic. So the network traffic to allow the machine to report itself out, to do all the things it has to report out, is about 350 bytes. And most networks should be able to handle that for routine, bringing this machine online. So this is a medium report. And here what we're doing is we're going to collect data about the TPM, more data. But voila, you go from about 350 bytes network traffic to about 560. So you're still a half of 500 bytes, 600 bytes. And you've got a lot more data about what's going on inside the PC and so forth and so on. And this is sort of lists off the data you get and so forth and so on. And this is generating a large report, okay, which if you do the numbers is about 750, 800 bytes. Okay, that's the big report. Okay, So you get lots of nice stuff out of this, and you're generating almost no network traffic to do these things. It's just crazy. That's it. Yes. I can take questions.
Looks like it's fairly straightforward to outsource the central distribution to a trusted manufacturer. So most companies want to drop ship from the manufacturer, and it seems like you do all that right there.
Yeah, so the rule really is simply that there would be three. It's just a security model. It just says there's central distribution with this level of security on it, and these secrets never leave central distribution. Okay. And then there's the fielding site with this level of security, and these secrets never leave the fielding site. Okay. And then there's the PC itself, and this guy's password is the PC. Okay. So how a given company or organization divides that up, it really doesn't matter. The architecture of the TPMs and the SEDs really dictated the fact that there's three natural locations and three grades of secret about both things and so forth and so on. Are there other questions? So I had at least one disk duplicator company call me up and said they got it. So apparently there's at least one disk duplicator company out there that read the SED spec and have put it into they can now duplicate SEDs, which is, I don't know whether they can or not, but they said that they can. So
question on the key derivation that you showed right at the beginning. I guess two questions. First one was the EK. It wasn't clear whether that was shipped by the motherboard manufacturer or it was created at the central site. And the second question had to do with the derivation of AIK.
So the central, so let's do one at a time. The central distribution is really a security model. So whether what you're saying was it happens in manufacturing or it happens, it really doesn't make a difference. What's required is that EK be created in a high security environment. And so if the manufacturer of the TPM ships a certificate with the TPM, you might have two pieces of central distribution. You might have the manufacturer's part of the central distribution and the contractor that does the other stuff to be the other part of central distribution. It's just a rule system of what's required for those environments.
The second part of that question was the way the AIK was shown as derived. It seemed to come only from the organizational certificate and not from the manufacturer's certificate. So
right, it's required that it be done in central distribution. So you create the identity of the motherboard in central distribution, and you have to have the owner auth password to do it, which is you can't just create an AIK at will. You have to have the right password to do it. Any other questions? So as I always say, several people know this, is there's no, I think you get 2 minutes of free time, okay? When I teach, I always like to make sure that my class gets out a couple minutes early. Makes them happy. So, thanks.